Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 12. Student, basically in lecture number 11. Okay, that was lecture number 11. Yes, this one. In lecture number 11, basically we cover the theoretical portion of the shear reinforcement in the case of flat plates or flat slab system with some new criteria of ACA code. Basically, I have covered this section of the flat slab system, how to control and how to design for a shear reinforcement in a flat slab system in this lecture number 11 and lecture number 10. Okay, it is available in my YouTube channel. Go to DDM playlist and here you find this lecture number 11 and lecture number 10. I thoroughly explain basically these lectures which you right see here, the design of basically for punching shear and the complete concepts regarding the punching shear, how to design for shear studs, how to design column capital, how to design drop panel, what are the criteria of drop panel, and similarly this lecture how to design a drop panel and what are the criteria for integral beam design. Thoroughly I explained this example. Okay, and in today's lecture we will see the design, okay, of the shear studs. Okay, but before that, as I already shared this video, okay, in the lecture number 11, that what is shear studs and what are the purpose of shear studs, okay, and why we provide it, what are the layout, and what is the head, what is stud rail, okay, and what is the advantage of using shear head reinforcement, shear stud reinforcement as compared to stirrup reinforcement, shear stirrup reinforcement. Okay, so we thoroughly see its design, its theoretical portion. Okay, what are the limitations of ACA code on these studs, and in today's lecture we will cover the design. Okay, some examples. So these are the portions which we covered in lecture number 11. Okay, what are the different cases, okay, how to calculate tributary area for punching shear for in case of one-way beam shear, and these are all about, we covered some example as well, but in today, that is lecture number 12, okay, we will cover some 3 to 4 examples over the design of shear stud reinforcement. Okay, so here we have this example. Okay, this is example number 13 for 12. Okay, and here we are not going to consider the moment transfer. This is very important. Okay, I already explained it. Inshallah, in next lecture, that will be lecture number 13. Okay, we will consider the movement transfer, but here, okay, I am not considering. Okay, those lectures will be more complicated if you don't watch, okay, these lectures and lecture number 11 and lecture number 12 which I uploaded to, which are basically in relevant of the equivalent frame method, relevant to equivalent frame method. This lecture is also relevant with the direct design method, remember. Now this is the example number 5, flexure reinforcement, 14-inch square column, 20 feet center to center, 22 in north east west direction, live load is given, FC frame is given, and what we have to do, we have to basically check the shear reinforcement using shear head studs, use the load and resistance factors if necessary. Okay, you have to check the capacity of the interior slab system column connection if necessary, design shear reinforcement using headed shear studs, as you see in this video, this kind of shear studs. So first of all, we have to select the critical section. Okay, so critical section basically already we explained in lecture number 11. We have inner critical section, outer critical section, and we already see how to calculate the average in that lecture. So go there and watch how to calculate d average in case of shear studs. Then the inner critical section basically it lies a distance of d by 2 from the face of the column. So this is the distance at which basically it exists. Remember in that lecture we also covered some part of this design which is done by the Dr. Khasrali, integral beam design. Clear? So here we have this example, and let me explain here one thing, that the position of the critical section. Okay, so here you see for an interior column this is the critical section, and from the face of the column it exists the distance of d by 2 to this side, d by 2 to this side. So the total this side it will be, as we have 14 by 14 inch column, this one and this one, 14 by 14 inch column. So the critical section parameter will be 2 times C1 plus D plus 2 times C2 plus D. So you already know what is C1 and what is C2. This is C2 side, in this case this is 14 inches. So 14 inch and D we already calculated. Here it will be D average. You will find the beta naught or B naught. Clear? And this is the, I think so, the diagram. This is 14 by 14 inch plan view. This is 20 feet and this is 22 feet. Okay, in this side. So we have to design for this interior column. Clear? So we have to find out the tributary area for this, and I already explained how to find out the tributary area for interior column in case of beam shear, in case of punching shear. So go there and watch that lecture. Now this is the procedure how to find, you already know it, and one side of that critical section will be 20.1. okay, so what does it mean? That this one side this is basically 20.1. so if one side 20.1, so we have four sided, so multiplied by 4 you got beta naught. This is simple in case of square column. Then we have to find out the enclosed area. So what does it mean? Basically we have to find out this dashed area. I already explained this in that lecture number 11. Okay, we have to find out this. So how to find it? Is a square, so one side is 20.1, so you just multiply it with 20.1 and divide it by 144 to convert it into square feet. Clear? So you got 2.81 is the area in between the critical section. Now we have to use the load combinations, and from this equation, this is the governing equation, we got 240 psf. This is our QU. So we have to find out our VU. So what is VU? So this is the tributary area minus the critical areas. We already explained this, that okay, we have a critical area, this one. So find the total area, which is this side will be 20 feet, okay, and this side is 22 feet. So 22 times 20 minus this area, and we already calculated is 2.81. So subtract it, you got your VU. Now you have to compare VU against this equation. So we know VU. So pi VC we already know it. VS for the time being, let's say, remember this will be the pattern. In this pattern we will provide our stud reinforcement. This inclined dimension is L2, and this dimension from the last stud to the face of the column, this is LS. Okay, this is LS, and we will calculate this 24.1, Remember, the face of the column is L1, which is 14 inch, it is given, and we will find out this total dotted, you see this dotted peripheral distance or peripheral circumference, you can say, this parameter. So we will calculate this. Okay, we will calculate this. Now we will calculate this SS and this d by 2. But remember, this L3 is given, L1 is given. So this side and this side, we just need to find this inclined side. And this is outer critical section. We have two sections. This is inner section, inner critical section. Clear? And remember, this L2 will be 2 under root times LS, this distance. And 2 under root, this is, I already proved this equation in these lectures. Okay, so go there and watch that lectures. Now we already know that in case of punching shear, when we have no shear reinforcement, remember I already thoroughly explained, when you have a shear reinforcement, we don't use this 4, we use 2. And why? The answer is in that lecture, that is lecture number 11. Why we dropping this punching shear capacity of the concrete to 50%. Okay, this is a very big question, and I answer this question in that lecture. Now this is now the punching shear criteria, but okay, if you are not providing shear reinforcement, if you are providing, then it will be 2 times. It means you have to divide it with 2. Okay. Now thus shear reinforcement is required in the critical shear section using studs, so that's why we have to use this one, and I already explained this in lecture number 11. Why we are using 3 lambda. Okay, in case of shear stud reinforcement, we will provide 3 lambda, and if you have a shear reinforcement by stirrups, you will use 2 lambda. Now your Vs, now from that equation, okay, here our Vs can be determined. Okay, this is simple, Vu minus Vc, okay, and divided by P or pi value, and from that we calculated our Vs is now 46.4 kips. So this is the limiting value that our Vn should be checked with 8. Remember, in the case of stud reinforcement, if you are providing stud, if you don't provide stud, then this value will be 6. I already explained this in lecture number 11. So this is 187, and remember this pi Vn, our calculated Vn value, which we not calculated I think so yet. Vn pi Vc, yes, 46.4. so we doesn't calculate, because Vn should be, pi Vn should be compared with the Vu. So Vu is where, this one, this is 105. So you see, we are well above. Okay, so that's why, if for example this pi Vn is more less than, okay, is less than your Vn, less than if it is greater than Vu, so okay, if Vn is less than Vu, so this will result very heavy shear reinforcement, very close shear stud spacing, and it will causes the congestion problems. So that's why we avoid such kind in such cases. Okay, now based on experimental, okay, I already explained this, that we don't use this value, we will use 2 lambda value. If you use 2 lambda, you got 77.6. so go there, watch that lecture thoroughly, okay, because I don't repeat things. Okay, here, so our Vs becomes now 77.6 kips. Okay, our Vs, okay, already our Vs, which is calculated, is 46.4 kips, but it is on the basis of 93. If we divide this by 2, so then we will got V is 77.6. Now you see V is increased. Okay, V is increased because we decrease 50% the shear capacity of the concrete. Layout the punch and shear reinforcement, as I already explained here. This will be the layout, and now we will use head to trial rule. Okay, trial and error procedure. Here they assume 8 stud rails. 8 stud rails. This means 8 stud rail means 1, 2, 3, 4, 5, 6, 7, 8. 8 stud rails. Remember, we have one. Remember, we will consider first of all this periphery. And in this periphery, you see we have 1, 2, 3, 4, 5, 6, 7, 8. 8 studs. We will find the AV of the studs. AV will be 8 times the stud area of stud. Okay, so the area of the stud we will now fix it. Okay, now you see we are using 8 stud rails, each with 7 1/2-inch diameter stud. Okay, AB area of 1/2 inch is 0.20 with 1.6-inch diameter heads. Okay, I already explained that we have a stud shaft and we have a head of stud, which is recommendation says that it should be 3.2 times of this diameter. Okay, so we are using 1.6-inch this stud diameter because it increases the effectiveness of stud reinforcement. Clear? Now, and the FYT of the stud will be 51 psi. Okay, we already explained it in lecture number 11. The spacing to the first set of shear stud S0 is to be taken less than or equal to d by 2. Thus S0 is 3 inch. Okay, you see here this one. This is S0. It should be less than d by 2 or 3 inch, I think so. Okay, these are the LCA criteria. Now the next thing is this, that before proceeding to layout the subsequent rows of shear studs, the shear strength should be checked at the inner critical section. In equation 1329, the area provided by the inner row of the shear stud is, I already explained this. This is now the total shear stud area along the first periphery. Okay, this one. These 8 studs will give us 1.6 square inch area. So now we will use this equation. I already explained this equation. Vs is this one. Okay, we will find the strength of the stud, which is basically provided in the one peripheral row, which we already explained it here in this one. So what will be the V strength of these 8 studs now? It can be determined by just multiplying this AV with the strength, that is FYT of this stud. So we got here what this one 81.6. So 81.6 basically exceeds 77.6. So our design is okay. Clear? And we will use spacing of 3 inch. Okay, and 1/8 inch diameter head. Clear? And 8 studs per row. Now the outermost studs are at 3 inch plus 6 times 3. Now 6 means that basically let me explain it. Okay, not this one. You see we have to place here 7 studs. So if you are placing 7 studs, the spacing in between these 7 studs will be, how much will be? 6, remember. Okay, because you see, if you are placing 7 studs, 1 2 3 4 5 6 and 7. So here 1 2 3 4 5 and 6. So we have 6 spacing. So we have to multiply this with S. This is basically S, and it is fixed that S equals to 3 inch or D by 2. Okay, now the purpose of this calculation to find out this LS. Okay, remember this outermost periphery, you can see this stud should be placed at a distance of D by 2. So this is 3 inch. Clear? So what will be now this distance? This distance will be, here you see the calculation. 3 inch plus 6 times 3. So that 3 is basically that from the outer periphery. Okay, from the outer periphery, D by 2 is basically 3 inch, and to the outermost stud. Okay, and we got the 21 inch from the face of the column. Now, and the outer critical section is 21 plus DO2. Remember, this 3 inch is basically S0, while now they're adding D by 2, so it gives us 24.1. okay, this is S0. okay, this is S0, and now they add that outer distance. Let me show you here. You can see we are interested to find out this distance. Okay, because this distance is important for us, so we need to find out this distance, okay, which is up to the outer periphery. This is the outer critical section. Now the distance from the last stud to this, it should be D by 2. So this D by 2 plus 6 spacing we have. So D by 2 plus 6S plus we have to this S0, and this is not is 3 inch. So you got 24.1 inch. Okay, write this value. Now you have to find out this B0. We are now able to find out this B0. Okay, and this will be those, remember, this L1 plus this L3. So we already know 14 inch right here, right here, right here, and right here. So we have 4 times 14 inch, and we have to plus it with this incline, this incline, this incline, this incline. So 4 incline distance. Now you see this is L2 is equal to 2 under root equals to times LS. So we already find LS. We have to just multiply it with 2 under root with 4. Mean that 2 LS. We got our B0. Clear? This is the whole summary of this calculation. You see here. And this is 192 inch. Now the area inside this line, will be 2710 inch square. So how they got this? So it is simple. Okay, it is very simple. If you see some mathematical background, you see we have this rectangle right here. So what will be the area of this rectangle? We already know it that this is 14 and this side is 24.1, and we have this kind of rectangles 1 2 3 4, so we have to multiply it 4, and we have 4 triangles right here. You see this triangle, clear, this one. So here we see this triangle, sorry. So the area of this triangle will be half times this distance into this distance. So this distance 24 and this distance also 24. So we have 4 triangles. So 4 triangle area plus 4 rectangle area, it will give the area under this outer critical section. Okay. So here we have, okay, here we have 2710. So you see this is the triangle area, and this one is the rectangle area, and this is basically the area of column, because you see here we have a column, so we have to count for this column area as well. So it will give you the total area under this outer critical section. Okay. Now, once you got this area, okay, inside that line, you have to check the shear stress basically. So VU will be now, okay, our VU will be now 240. We already calculated. This is the total tributary area for interior column, and now this is the area, okay, which is for the outer critical area. Remember, we have to check the shear capacity for first inner critical section. Okay, this is for inner, and now that is for outer. 101 found. Okay, now the shear stress, this is shear stress VU. Okay, this is the shear stress. So shear stress divided by B naught into D. This is the shear stress in PSI. There are limitations that this shear stress should not be more than, okay, the shear stress on the outer critical section is limited to pi VC. That is, now you see we don't multiply B naught into D. Now you see 94.9 psi. So here we are safe because our VU is less than, okay, our pi VC. But here remember, this is stress, not shear. This is stress value. So the acting shear stress is less than the capacity of the section. So that's why our final design will be what? Try 8 stud rails with the first stud located at a distance of 3 inch from the column, and subsequent will be 3 inch, okay, and 1 or 2 inch diameter with a 1.6 inch top head reinforcement. Okay, this one. So here it says 1 2 3 4 5 6. We have to add one more, it becomes 7. Okay, let me draw here to understand it practically. Okay, why not it works? I think so it doesn't work for, yes, now it works. Let me show you here. Okay, we have, remember, we have one stud here, okay, one stud here. So we have this distance is S, which is 3 inch, Now 1 2 3 4 5 6, we have 6 spacing, and here from the face to the first stud it is S naught, okay, and this is 3 inch as well. Okay, so 3 inch plus, now remember this distance from the face to this one to the last stud, it will be S0, that is 3 inch plus 6 times S. You see here this one. Okay, remember this one. Where it is this one. Okay, plus, now see, we have to find out, remember, the dotted area or dotted section. Okay, now this last stud should be located from that outer section at a distance of d by 2. Okay, so the total distance, now this one, that is denoted by ls. Okay, this distance plus d by 2, and it comes out to be 24.1 inch. Okay, so here we have 8 rails, means that this rail, this rail, this rail, this one, this one, this one, this one, and this one. We don't have these radial rails. Okay, if shear capacity is more, so we can provide these radials. Okay, but at this time we have these 8 rails, and at each rail we have to provide 7 studs of diameter 0.5 inch, and this head is 1.6 inch. This is the final design. Now next what we have next question, and in this question we have 7.5 inch thickness, 6 inch effective depth, and carry 12 inch square column, 15 feet on centers in each direction, a factor load of this much, and typical interior column. Concrete steels are this. Determine if shear reinforcement is required for the slab, and if so, design integral beams with stirrups to carry the excess shear. I don't discuss it, but you must remember, because I already explained this in these lectures. So go there, watch this lecture number 11 and 10. You will understand how to design an integral beam. But at this moment, the design of integral beam is very important. I already discussed this design in my lecture number 11, and I show that when you have, remember, this is around about 13-14 story plaza. So if you have such heavy structure, in that structure punching shear governs in the interior columns, and there is enormous amount of shear, punching shear. So how to control in such situation? You have to provide integral beams, and the design, you must be able to design an integral beam. So I thoroughly explain in this lecture number 11 and lecture number 10. So go there and watch those lectures. You see, pi VC is this one, and pi VN is 122.9. This is the final design. You see here the outer parameter. The principles is same as we discussed for the shear studs. Only difference you see 8, where we in that case we use 8, here they are using 6, and yes, the rest of the things are same, I think so. Nothing could be changed. We will use this 2.5, not that value, remember, for design purpose if shear reinforcement is needed. And we have to calculate spacing, clear, and but this spacing should not be more than d by 2. And then now in the case of this, we have to find out b naught. Okay, we have to find out b naught, and how to find out b naught I already explained it in those lectures, and it is also available that you have to equate bu with pi vc from this you will be able to find your B naught. Clear? I think so. Here you see, you have to compare VU pi VC, you can find out your pi VC, B naught. Okay, so next you have to find out your R and then the whole outer area. Okay, and then you have to find out your shear stress as we did in that example. So this is the whole procedure. Okay, I just give you an idea. Now it says here in this example that repeat this example okay, using head stud reinforcement. Try number 5. Bar will be used negative flexure reinforcement, and we already know about this. So this is the layout. Okay, and how to calculate the D average in lecture number 11 I explained this. Okay, and this is the final reinforcement. Add studs on periphery. Okay, add studs on each periphery, and this first interior critical section is B naught, which is 72 inch, and the last one, okay, this is 228 inch. We already calculated this in that example, in previous example. Now 1 at the rate of 2 inch and 6 at the rate of 4.5 inch. The first one will be placed at 1 inch distance, 2 inch, and then the rest of the one will be 4.5 inch. So total 7 studs will be used. Okay, so this is the design. A stud height of 6 inch will be used. This is okay, which is consistent with the effective depth and exceeds the minimum requirement as in example 13.4. The design shear strength of the concrete alone at the critical section will be this one. Now this is the punching shear capacity without shear reinforcement, remember. Now the VU, which is already calculated in the previous example, is 120 kips, indicating that, remember, VU is more than pi VC. This means shear reinforcement is needed. Now if you are using stud reinforcement, we will use 8, not 6. Okay, and if you are using stud reinforcement, we use 3, not 2. Clear? And the maximum spacing between the stud rails must be less than 2D. So 2 lines of studs are needed for a 12-inch square column. This 2D means what? This is important. Remember, ACA code criteria says that this distance should be less than 2D. 2 times of D. Clear? So this is 12-inch column, and I think so the D is 6 inch. So 2 times 6, you got 12 inch. So 2 lines will be provided. Remember, 2 lines will be provided. These are the ACA criteria. So 2 lines of studs are needed for a 12-inch square column. A center to center spacing of 11 inch will be used. Now this distance is now 11 inch. Okay, this distance is now 11 inch center to center, and the shear stress in the slab in the first critical section is approximately 4.4 FC prime under root, which is below, okay, 6 FC prime under root. What does it mean? This means that if you multiply this is the ACA code criteria. Basically, I already explained this in lecture number 11, that if your 5EC value, 5EN value, sorry, below than this value, your maximum spacing will be less, should not exceed this value. And if it is more than this value, so your maximum spacing will be 0.5 times of D. Okay. This is, so go and watch lecture number 11. So the spacing will be 4.5 inch maximum spacing. Okay, so the maximum spacing is now fixed and equal to the maximum. Okay, so this is the maximum spacing. I already explained this in lecture number 11. Okay, how what does this equation means. Okay, now we will find out the AV. So how to find out AV? We already know this equation. We find out the S value, and this is phi fyt into d. Okay, phi fy and d we already know. So this is our required shear area. Okay, a peripheral line of studs contains 8 studs. Okay, they contains 8 studs requiring a cross-sectional area of 0.14 inch square per stud, or 0.5 0-inch diameter. So if you multiply, let's say 0.2, okay, the area of the number 4 bar, okay, or 0.5 inch diameter is 0.2 times 8, we got 1.6, and 1.6 is more than 1.15 inch square. And you see here in one peripheral line we provide 8 studs, 1 2 3 4 5 6 7 8. Okay, so this is more than that value. Okay, so we will save here, okay. So the next thing, we just need to find out the 5BC. Okay, what will be the design now, the strength of the section, and we need to find out B naught. Sorry, so how to find out B naught? See, we have to compare this 5BC with VU, and VU is basically this one in found 120 kip. Basically we already determined this one. So just equating this one, we already know the value 2 lambda fc prime under root B naught into d. We already know d, so find out B naught. So once you find out your B naught, that is 211 inch. So 211 inch, the first stud is placed at a distance of 2 inch, which should be fulfill this criteria. From the column face, 6 studs at a spacing of 4.5 inch provide a minimum perimeter of 228 inch. Now how they did this calculation, you have to come here again and repeat the same calculation as we did here, and you have to follow same steps right here as we calculate VU, VC. Okay, if your pi VC is more than VU, the design is okay. And how they calculate B naught, so you have to repeat this procedure. Clear? You have to find out your inclined distance as we did here, the short distance. Now in that case we provide S naught equals to 3 inch, but in the last example we are using 2 inch. This spacing here we are using 3 inch, but in that case we are using 4.5 inch. So I thoroughly explained the whole procedure right here, right here. Okay, I find out this LS, then I find out B naught. So go for the same step. Okay, there you see the steps are not fully explained. Okay, they just say B naught is equal to 211. So how they got this value? Okay, they use this approach, but you can use the same approach as we did in that example. Okay, so this is, you can say, another way that you can do the calculation in this way as well. This is end of this lecture. Okay, we thoroughly explain how to design a shear reinforcement in the case of flat slabs with different options, integral beam and as well as shear studs. Okay, and in next lecture, okay, which is the most important lecture, okay, and that will cover the shear the unbalanced movement transfer. Okay, most of the students basically ask this question: how to design a column, eccentric column, edge column, or you can say the corner column, because there are loading, shear and movement. Okay, so which is known as uniaxial column or biaxial column. This is very interesting topic. It will be a very interesting topic, and this will be a very important lecture, okay, for those students who ask these questions, and very important. Okay, so see you in next lecture. Thank you for watching.